Today we'll talk about machine cycles and loops. So in this lecture we'll learn um, how can we use our instruction set and calculate the machine cycles of the instructions so that we understand that how quick our our instructions will be executed by the microprocessor. Okay. Now again, as you probably know that any microprocessor generates a bunch of clock cycles, and it actually keeps generating the clock cycles. So if you look at here, see as an example, if you have a 2 gigahertz microprocessor, that actually generates 2 giga, meaning 2 times 10 to the 1 9 cycles per second. Now what are the cycles? Now this is the cycles. I'm sure that you all know about the pulses, right? Like the square shape, signals. So any microprocessor actually keeps generating a signal like this. So this is just 0 and this is 1. So again it goes all the way up to here, then becomes 0 and then again 1. So basically from starting from here to here, that's like a complete cycle. That's just one single cycle. Now think about a 2 gigahertz microprocessor which will generate a lot of cycles in 1 second. Okay, no matter whether we use the cycle or not, the microprocessor keeps generating the cycle. Now what is the point of generating these cycles? These cycles are actually like the energy microprocessor has or produces, so that the instructions that you are running, your program is running, are using these cycles. So for an example, if you look at this, for an example, this is an instruction, right? Like an immediate LDA $25 pound dollar 25 immediate instruction. This actually takes 2 cycles to execute. Okay. Now think about the microprocessor. Let's say 2 gigahertz microprocessor. It actually generates a lot of cycles, and this instruction only takes 2 out of that many cycles in 1 second. So which is like extremely fast, right? So that actually gives you an indication that how quick your instruction will be executed by a 2 gigahertz microprocessor. Now in this lecture we'll learn how to calculate the machine cycles, how to find it. Okay, so for an example, remember I just said that this instruction will take 2 cycles. Now how did I know it? I just knew it from our instruction set. If you go to our instruction set right now, in the column 7 you are given all the machine cycles for every single mode of the instruction. Now remember, every instruction has several modes, right? Meaning every instruction, let's say, may support immediate, direct, extended, inherent, like even indexed, and then we have another one which is relative, right? So these 6 different cycles has something. These 6 different addressing mode has different cycles. So for the same instruction, if this is immediate, that will be a cycle. But if it is direct, it will be a different cycle. I'm saying that's actually defined by how the architecture of the microprocessor is inherent and embedded and designed. Okay, so that's pretty much like predefined, and we cannot change it. Now, to understand and calculate the machine cycles, you need to know 3 different things. Number 1, addressing mode. And I'm sure we will all know the addressing mode, right? Just by looking at the instruction, we can tell what is the addressing mode. And that's pretty straight, and we already know it. Number 2, machine cycles required for each instruction. We can also know it very easily just from the column 7. So that's pretty much like given, okay? Now, so the first 2 items that we need to know, we already know it. But what we don't know is the third one, which is pseudo-op. Now that's something we probably have never heard before. So we'll talk about the pseudo-op in this lecture. That's not, I'm saying we already know about the pseudo-op. I'm saying we already have seen pseudo-op, but we probably have not realized that these are pseudo-ops. Okay, so we'll talk about the pseudo-op, and then we'll show you some codes so that you can see how we can use this information to calculate the machine cycles. Okay, pseudocode are some sort of commands that we use to direct the assembly process. So basically, we use the pseudo-op to tell something to the assembler. Okay. Now remember, the pseudo-ops are not part of your instruction set. That means these are not something specific to Motorola microprocessor. So no matter what microprocessor, what instruction set you are using, you will always have some pseudo-ops, which is pretty general, okay, general to your assembler. So, and these are interpreted as control information to assembler rather than assembled into machine code. So these do not have like machine code, okay. I'm sure that you have seen the pseudo-op. Let me show you one, then you'll probably know which are the pseudo-op. Now my first one is ORG. Now think about the ORG. You pretty much start any program with ORG, right? You just say, oh, ORG and then address. So that is how you actually tell your assembler that dump or deposit the following code starting from this address. So technically that is not something from Motorola, okay? That's like that's like something very specific, very generic and used to give some command to the assembler. So as you can see, if we write this, that means that you are just saying the start from the following, start depositing the following machine code, meaning the next lines of code starting from this address, right? E150. We have several other ones. I'm sure that most of you already have seen all of these. So another one is like EQU. Remember in the lab 2 we used EQU, okay? Now this is like a symbolic label to used to a numeric value. So for example, what happens, a lot of times you probably will be using a lot of numbers in your program. For an example, very soon you will see that we'll be using the ports that we have with our Fox trainer board. Now every port has a predefined address given by Motorola. Now there are several ports, and you don't want to memorize all those addresses because those are something like predefined, but you don't want to memorize. So instead, what you can do is, if you just write something like this, for an example, port B, EQU, and then this is the address of port B. And after that point, every time you write port B in your program, your port B is actually will be replaced by 1004. Now what is good about this? The good about this is it's much easier for us to to write port B instead of writing the address of port B. Because address are some numbers, right? I'm saying it's like hard to memorize all the numbers. Think about your cell phone, right? I'm saying instead of just having your friend's name saved, if you have been saving all their numbers and then try to recall them just by their numbers instead of their names, it will be very exciting, right? I mean, this is pretty similar thing. But the EQ is like a assembly directive that actually helps you to do it. I think we already have used EQU in lab 2, but we probably have not realized that this is a pseudo-op, okay? Now there are several other. For an example, I'm sure that you will use this one in lab 1, FCC. This is, somebody, I think we already talked about this one day in the class, that form constant character. This deposits a text string into an object code. So for an example, anytime if you have a string of character, right, like this one, enter text, I'm sure you have seen it, right, in lab 1 and maybe in some other lab as well. So for an example, this is like a pointer to text. Remember in C++, you can use like pointer to string, right? It's something similar to that line, okay? So this is something, again, you probably have used, I'm saying you have seen FCB. You probably have not seen FDB, but you have seen FCB. Now FCB and FDB is pretty similar, that actually deposit a single byte or word into object code, okay? Now, what that means? That actually means this. So if you write SB1 FCB A5, that means you are trying to save these for this variable. Now this is pretty similar like when you define a variable in C++, what do? At the very beginning you write, oh, integer x equals to 5, right? This is pretty similar. So this is your integer x, and this is the value of integer x. Now, something is different in low-level language, because in the high-level language we have plenty of different types of data, different data types, right? We have integer, we have double, long, we have character, we have many other variants of data types. But in the low-level language is actually all numbers. It's all binary numbers, and then when you write in the in the program, you actually write it in hex. But again, that's more handy. So you pretty much save everything as in terms of hex number. So for an example, if you look at this DB1, that is from double byte, that means this is just a double byte instead of just one single byte. Okay? And again, don't forget, these are like, anytime you write this variable, these variables will actually hold the address of those bytes. This is interesting. Look at this. This is a byte, right? A5. Now, remember the A5 is a data, right? And it must be saved into a location, memory location. So that means A5 must have an address. We don't know what is the address at this point, but A5 must be saved in a location, right? So there will be an address. So anytime you write SB1 in your program, SB1 is actually replaced by the address of A5, not by A5, okay? But I'll show you some more example that will give you some, this is interesting. So, think about this. So if you just write SB1, that actually is like an address of A5. And same is here. If you write DB1 after this line, that will be the address of the first byte, because there are 2 bytes, right? And you cannot hold the address of 2 bytes together, because I'm sure that C0 will be saved in 1 byte and A08 will be saved in the next memory location, right? So DB1 will hold the address. I'm saying DB1 it represents the address of the first byte, meaning which is C0. So we have some more. I'm sure that you have seen this one in lab 2 as well, RMB, reserved memory byte. What this does is, a lot of times what you do is you start a program from somewhere and then you try to save a bunch of memory location, and you try to reserve a bunch of memory location for something else you will do in future, okay? So RMB means reserved memory block. So you can pretty much block a bunch of memory location just by doing that, so anytime, let's say you write RB1, again, RB1 is a label, okay? Don't go by RB1. You can just put whatever name you want, okay? This is just a label, just like a variable name, okay? Then if you just write RMB and 20, that means you are trying to reserve 20 consecutive bytes. So it will actually block that. Now, what do we mean by block? That means it will actually skip those 20 bytes and then it will again do something else. Now, later, if you really try to use this memory block, you can always use the RB1 and save something there, right? Remember, if you go back to lab 2, you probably can recall that in lab 2 we added 2 numbers. We wanted to do a multi-precision addition, right? With decimal adjust. So remember, we had 2 numbers and then we wanted to add and we wanted to have the sum. But to save the sum, we already reserved 3 bytes at the beginning. Remember S1, S2, and S3? We actually saved those 3 bytes using the RMB. We reserved those bytes, but later on, when we actually added and got the result, and we went back to those locations and saved the answer. Okay? So that's how you can always tell your assembler, oh, save some byte, we'll use it later. Okay? This is again pretty much similar. What do you do in the high-level language? For an example, in the high-level language, a lot of times you define a variable, but you do not use the variable until some, until some point, right? Let's say you just define integer x. So you don't know what is the value of x, but after a bunch of code, you probably use x. So until you use it, so you're pretty much like reserving, some bytes for that variable. This is pretty similar, but this is more powerful in the sense that in the high-level language, you reserve integer, which automatically reserves like 2 bytes. When you define variable like character, automatically reserves 1 byte. But now you have more freedom of reserving. So that means you can actually reserve as many bytes as you want. Think about the high-level language. You can reserve 20 bytes. I'm saying just for nothing. I'm saying you can just say, oh, I want to reserve for integer. So your program knows integer means 2 bytes. It knows, oh, double means 4 bytes. I'm saying it automatically just uses that idea. But you cannot customize it that much. I'm saying now you can just use a 20 byte without saying what it is or what exactly you need it for, right? Now, again, I'm sure that we have seen all of those. Now, let's see couple of lines of code. There is no sudo op right now, but we'll use sudo op soon. But I'm just trying to show you, let's say these are 3 lines. We pretty much know all these 3 lines and what is going on here. But can we calculate the machine cycles for these lines? To calculate the machine cycles, all you need to know what is the addressing mode of the line and go to the instruction set and look at the column 7 and find the number. Now, the first line, of course, is immediate, right? Second line, direct. Third line, extended. Now, if I go to my instruction set, column 7 for these instructions, you will actually get this number. So can we go to the instruction set and make sure we understand what we are saying, and can you find those numbers? In the column 7, for all of this instruction and for these specific modes, you'll find these cycles. Okay, that's actually pretty straight. All you need to know is this, addressing mode, and go to the instruction set and check the column 7 for the same instruction and for the same addressing mode. Then you will actually get this number. Now, once you have those cycles, then you can add the cycles. So for an example, you have 3 lines. So pretty much for these 3 lines, your total cycle is like 9 cycles. This is a very interesting thing, because just by these cycles, you can guess how fast this code will be running. Now, for an example, if you have an instruction set on your hand, can you check how many cycles you need for the instruction MUL? You know there is an MUL instruction, right, which multiplies 2 different bytes, right? How many cycles? So for MUL, your cycle is 10, right? Now think about this. These 3 lines in total is taking 9 cycles. But MUL itself, just one instruction taking 10 cycles. That means MUL itself will run slower than these 3 lines, because that is taking more cycles. It will take more cycles, then it will be more slower. You see what I'm saying? Now, the machine cycles actually is a very interesting information that you need to know to understand the speed or processing speed of your program. For an example, let's say a lot of times some of the operations are pretty equivalent. For example, if you add 2 plus 2 and 2 times 2 is the same answer, right? Yeah. But which one you do? Do you add or do you multiply? Of course you will add, because if you add, your cycle will be much lesser. Because if you multiply, you have to use MUL, which is much more expensive, right? So, see, the machine cycles will give you that kind of idea, that which instruction is even more. There's a lot of times you can do pretty much the same thing. And even, let me tell you a couple of things. Probably I thought we talked about this, but I just want to remind you. Remember at some point in the very first half of this class, we talked about those shift instructions, like you remember the right shift, left shift, those. Think about the shifting. Some of the shifting, like I think that's the right shift, divide the number by 2. If you do 1 right shift, it's actually like a division by 2. Now, think about this. You can also divide by IDIV, right? We have IDIV. Can you check how many cycles you have for IDIV? That's an inherent instruction, right? Wow. So would you use IDIV, or if you are just dividing by 2, you don't need to use IDIV. You just use the shift instruction. Do you see what I'm saying? Because shiftings are much less expensive than IDIV. I'm saying the machine cycles will give you those kind of idea that which one I should pick, right? I'll tell about the machine cycles again after a while. But let me first show you how sudo op come into play and play an important role in calculating machine cycles. Now, let me show you here that let's say we used a couple of sudo op here. So at the beginning we said start from 0010. That means we're just saying the next line will start from this address, right? What that means is this is a variable, right? A1, which is storing a data, 48. Now, can you tell me what is the address of this A1? Of course, 0010, because you just said start from 0010, right? You just asked your assembler to start from 0010. So the address of this A1 is 0010. Now, if I go to my next line here, can anyone here tell me what is the addressing mode of this line? It's actually hard to tell if you don't know what is A1. Now, think about the A1. This A1 will actually be replaced by the address of A1. Okay? Now, what is the address of A1? 0010, right? Which is actually just 10. So, this line is pretty much equivalent to the line you have at the right side. Now, just by looking at this line at the right side, you can tell, oh, this is a direct instruction, right? And then you can tell this is 3 cycles. So now you can see how pseudocode play a very important role when you determine what is the addressing mode. Because without the pseudo op, in this case, you can't tell what is the addressing mode. And then you cannot tell what is the machine cycle. Okay? Let me show you some more. So for an example, let's say we have some bunch of lines here, right? So you see, we just first said, oh, start from this address, and then we saved A1, and then we again started from a different location. See, this is much far later than here, right? This is just 0010, but next one is 1010. That's like far later, right? Now, what is the difference? Just for that, the first line is read like this, LDAA $10, right? Because address of A1 is 0010, which you can write just as 10, right? But address of B1 is 1010. Because you're just saying, okay, you said start from 1010, then you wrote B1, right? So, very interestingly, first line, the machine cycle of the first line is 3 cycles because this is direct. Machine cycle of the second line, even if that is a pretty similar instruction, the machine cycle is 4 cycles because that's extended. See how important the pseudo op is so that you understand the machine cycles. Let me show you even some more exciting one. Let's say if I have EQU instead of FCB, what happens now? For the same lines of code, now, do you see the change now? Because even when you are writing EQU, every single time you will be writing B1, that will be replaced by the value of B1, not by the address. So the value of B1 is actually 58. Now this becomes 3 cycle. This is really exciting. There are plenty of interesting things can be done just by the pseudocode. Okay? Just because anytime you write EQU, that will be replaced by the value of the variable. So the B1 was a variable, right? The value of the B1 is 58. What do you mean by the value? Meaning the content. Okay? And before that, when I was using FCB, that was replaced by the address of B1. See, every memory location has an address, has a data. We know it, right? That's completely, Now, I think once we see it, we pretty much can tell, just using the knowledge, a little bit knowledge from the pseudo op, how we can calculate the machine cycles in such cases. Any question? All right. I'm sure that we can wait for the quiz. So we just have one quiz for this part, so where you'll be given a couple of lines and then you just have to tell what will be the cycles, total cycles, okay? Now, we are not done here. We'll do just one more step now. So remember these 3 lines we just have seen in the previous discussion of this lecture. So, and we pretty much know that we have 9 cycles here, right? And we know how we got these 9 cycles. Now, in addition to this, if I ask you this question that, okay, now we know that these 3 lines are 9 cycles, okay? Equivalent to 9 cycles. Now, can you tell how much time is required to execute these 3 lines if our microprocessor is clocked at 2 gigahertz? We say very simple. All you need to know is a very small formula, which is total cycles divided by the processing speed. Now, the total cycle here is 9 cycle, right? And what is the processing speed? 2 giga, right? So 2 giga means 2 times 10 to the negative 9, 10 to the 9, right? If you do this that's a simple math. If you do that, it will be 4.5 times 10 to the negative 9, which means 4.5 nanosecond. Now, this is very specific. Just for this 2 gigahertz processor, you can tell these 3 lines will take only 4.5 nanosecond. Now, if your processing speed is much more faster than these, your runtime will be much lesser, right? Because the more, so that's the same reason why, when you actually buy a new laptop which has a higher configuration, it runs the same bunch of lines much more faster than your previous one, because now your microprocessor generates more cycles, just like this one. Okay. Now, for an example, if your microprocessor is like 6 gigahertz instead of 2 gigahertz, it would be running the same 3 lines just for 1.5 nanosecond instead of 4.5. I'm saying just do the math and then you'll know why it is. Okay. So now you can see why, think about, older days when we had like Windows 95, Windows 98, the booting time at that time and booting time now is still pretty close. Now probably we are having a little bit less time. But think about the codes we are running right now. Windows 10 probably is like even more than 5 times of code that the Microsoft wrote for Windows 98. But it is faster. Why? Because the microprocessors are even more faster than that time. And it's all about how many cycles the microprocessor is generating in 1 second. And there are many other things come into play, because it's not only about the generating the cycles, because they have to also control the heat, because every single thing comes with, heat comes like free, and then you still have to take care of the heat, and then you see how many fans and coolers and things you have with the microprocessor. There are plenty of other, they even build circuit to control those heat, there are plenty of other things. So we are just trying to simplify it to understand the very basic of how these things work. Okay. So I think after this lecture, it will be much more easier for us to understand how things run and how we can exactly tell how much time we need to run a couple of lines of code given a microprocessor with this speed. Okay. So again, this is just one more additional step which will be covered by our next quiz, which is quiz 22. Okay. Understanding this part of the lecture is very important and crucial, because it will actually help us to understand the loops and calculating the cycles for the loops. The difference between this code and the loop is, as you can guess, in the loop you'll be running a couple of lines for several times, right? Now, for an example, if one line has like 3 cycles, but if it is running for 3 times, then you actually got 9 cycles. So, again, those are pretty important to understand, and we'll talk about this very soon. So let's go to our quiz section and let's try to see how fast we can finish all these quizzes up to quiz 22. Let me stop this presentation here.